Hi, Emma. How are you? Jose, hi. How are you doing? Jason, how are you? Hi, Jesus. I'm okay, thank you. We have no class on Wednesday. It's a holiday. So we'll talk about what we need to do this week today. We'll wait a few more minutes for everybody to join. So if you can check out the assignments that we need today. And then we'll work on our assignment and then we'll talk about the lab. You can check out Canvas and go ahead and download your assignment. It's in Note. We'll go over that. We'll wait a few more minutes for everyone to join, okay? Okay, I'll go ahead and get into screen share. We have about another minute. So on Wednesday, we are celebrating Cesar Chavez Day. So there will be no school in session for Wednesday. for this week, we are going to work on Unit 7. And so if you can check out your notes and your assignments, and we'll talk about the lab, as we have no Zoom session on Wednesday, so that will be a homework assignment. And then I'll see if I can pull the video or put up the video for you in the case if we don't get it covered tonight. Then next week, we are going to cover Unit 8. And in Unit 8, we're going to go over some series and sequence or sequence and series. Excuse me. We have a homework assignment next week, and that's not going to be due until you come back from spring break. Then you're going to have a spring break that will be from the 12th through the 16th. And then we're going to come back and work on Unit 9, and I'll release the project then. Okay. So now for the spring break, if you are looking for something to do, let me move this down. And if you want something to do, MVC, I make an Innovation Center, they're hosting a hackathon on the 16th. It's going to be from 10 a.m. to 6, and you can register there and you can look at the flyers for information. So this will be a cool event if you want to participate in a hackathon. And so they will have little mini games, trivia games, and then you can work on project that will be for military applications. So that will be pretty fun if you wanted to join there. Okay. All right. So let's talk about what we need to do today. We're going to talk about algorithm analysis, and we're going to work on search and sort. So if you downloaded the notes, let me move this up. We are going to cover chapter 10. And at the beginning of the notes, it talks about algorithm. And I think we've been touching on how to solve some problem, looking at some of the things that is presented to you, and we can solve it mathematically and then apply that with the programming side. So this week, we're going to touch on how to search using C++ and how to sort and implement the general algorithm for search and sort. So algorithm is just a process, or it's a set of rules to be followed in calculations. And we can implement different solving operations or sub-processes to be able to derive a solution. And the areas that we are working on this week is going to be searching and sorting. And we will look at different type of search and sort. So now in search algorithm, we mainly want to find an object in a collection. And in C++, at the lowest level, we would use an array to store values or a group of objects. Then we would use a key to search for a specific object. And we can go about by doing a linear search, or we can look at ways to implement binary search. Now, each object would have its key value. And what we can do is we can search for that particular key. And what it's going to do is, based on the algorithm that you implement in the program, it's going to execute the search. So when you look at the container, we mentioned that we would use something like an array. And if you're more advanced in C++, you can use other type of container, right? You can use a linked list, you can find ways to organize your data, but at the lowest level, we would use an array. And in the array, each of the element you would have as index. Now, in an array, the first index would be 0, but let's say that you have the first element and you would have a certain value assigned to each of the element, and then you can go through each of the element to find the matching key. Now in that, what you have is you have a linear search where you would look through every single item in your container and be able to find a specific key. For the unordered linear search, the object in the collection is not ordered in any manner, so we don't have a pre-sorted. So the example that you see on this page, page 1 in the middle, you would see that this is a collection of objects, and we have 34, 16, 12, 11, 54, 10, 65, and 37. They are not sorted. They're not arranged in any manner. And if we're looking for 11, what it will need to do is it's going to need to iterate through each of the item or the value in the index and be able to seek for that number 11. So that means that it's going to go through the first 4 elements. When it gets to the 4th element, it's going to find the number 11 and it would terminate. So now in the case where if we're looking for 37, which is at the end of the array, it's going to have to go through the entire array to find that particular value. So in analyzing, we would see that we would look at the number of elements, right? And also in an unordered linear search, we don't have any kind of sort or arrangement in the way that we present the data in the container. So that means that in the worst case scenario, in the case of if we're looking for the last value, the last element, it has to go through the entire container in order to find that particular value. Now, for compare the unordered linear search to an ordered linear search, we would have a pre-sorted array. So that means that we would have to sort the value, or the value has to be manually entered into the container in a certain arrangement. Like if we were doing ascending sorted, that will be from smallest to the highest value. And so one would need not to necessarily search through the entire list for a particular object to determine that it does not exist. So if we can find the middle point, and we can say that from that middle point going backward from the beginning, that would be the lower value than that middle point. And so we can do comparison in such case. Now, from that middle point going forward to the right side of the container where it would be increasing to the higher value, then we can say that from that middle point, we can compare the value looking for anything that's higher than that middle point value. So now what we would see is that we can go from smallest to highest, and it would also terminate as soon as it's determined that the number is found. So if I'm looking for 34, right, and in this case we have 8 elements, what we see is that the middle point of this particular array is at after element 4, which is going to be 16. So anything above 16 will be higher. So what we can say is, to make it quicker, we can identify that middle value and use that middle value to compare. Now, we don't necessarily have to go through the entire container to be able to find, but with the ordered linear search, if we're looking for the last item in the container, we can identify the last half and be able to point to that because it's already prearranged. Okay. So it's slightly different than what you see with the unordered linear search, where the numbers are all scattered and there's no arrangement, compared to ordered linear search, where we do have a point where we can find what is higher and what is lower. Okay. So here it talks about how if we consider the ordered linear search in the array, and if we're looking for the number 11, the first two element needs to be examined until the second element contains. So it's still going to have to find, it's going to linearly examine the value. So it goes through 10 and it's not a match. And then it moves to the second element, which is 11, and it is a match. So then when it got here, it's going to say 11 is a match and it's going to terminate. Now, if we're looking for 13, right? So the next example, it talks about looking for the number 13. It would need to look through the first four elements. When it gets to number 16, it's going to say the 13 is not found. So in the case where if we're looking for a key that doesn't exist in the container, it's going to stop right at 4 because 16 will be higher than what the value that we're seeking. So that it's going to present that the value is not found, right? We would have the program display that value is not found. And in the ordered linear search, it doesn't have to go to the end in order to determine that, because in the arrangement of the container, by the time it gets to 16, it already know that 13 doesn't exist prior to 16. Okay, so that's it's slightly more efficient than what you see with an unordered linear search. So in this case, we have to have a sort in order to enter this search, and it would be more effective than using an unordered linear search. So for the first question, you don't have to put it verbatim, right? Based on what we talked about, we can look at the similarities and the difference of the unordered linear search and an ordered linear search. So in an unordered linear search, in order to determine that an object does exist in the collection, in the worst case scenario, it would have to search through the entire collection. Like what we talked about, if we're looking for a value, it has to examine every item in order to really see if that item exists or not. Because that item could be further down in the container. It's a later element in that container. With the ordered linear search, the array is sorted, or the container has sorted values. And what it will need to do is it's going to need to search. It doesn't need to search through the entire list to find a particular object. It can stop sooner if the search key it belonged to the first half of the actual list. Like what we talked about, 16 is the mark of the middle of that container. And so if we're looking for 13, it will stop at 16 and it should output, right? 13 is not found, instead of going to the end of that container. So it tells us here that while scanning the array from left to right, from smallest to the highest value, the search can be terminated as soon as it's determined if the number can be sought. And what we see is that it would then compare the key value to the element that's currently examined. Okay, and you can find the verbatim information on the notes as well, but you don't have to put it word for word. You can summarize it. So then when we look at the linear search, we have to think about the number of elements that exist in that container. How many elements are we examining, right? In the case of an unordered linear search, if you have 100 elements, it has to go through the entire list. In the ordered linear search, it depends on your key value that you're looking for. So let's say I have from 1 through 100, and I'm looking for number 31. Well, what it can do is it's going to go through the first half. If 31 actually exists in that container, it's going to terminate at 31. And if 31 doesn't exist in that container, it's going to terminate at the midpoint when, or the value that's higher than 31. Let's say 40. Okay. Any question with linear search? So when we analyzing this, your function would be dependent on the number of input as we would apply iteration for the programming side of this. Okay. So if you have 1,000 elements, your n would be 1,000. Okay, so your f of n is going to be n. Now, linear search is not the best algorithm, but it's the simplest, right? It's the basic to, and you can have it implemented with the loop and then be able to loop through. Another way that we can search is using chunk search. Okay, and in this particular textbook, they refer to this as chunk, right? In other areas, they might refer to it as jump. Okay, so chunk search, what it would do is it would take the container and divide it up into subsets. Okay, and it would divide it up into chunks. So each chunk is going to be the square root of your input. So let's say that I have 100 elements. So to chunk it into equal chunks, it's going to take the square root of 100, which gives me 10 elements per chunk. Then with the search key, it's going to look at the maximum value in each chunk. Okay, so what I did here was I highlighted it. So the first one is the orange. Okay, so in this case, the example that we see here, we have 8 elements. Okay, and so if you take a square root of 8, what we can look at is we can round that up, right? So visually we can see that it would chunk, it would do the first 3 for one chunk, the next 3 for the second chunk, and then the last 2 for the third chunk. So let's say that if I'm looking for the number 13 again, what it would do is it's going to evaluate the first chunk maximum value, which is 12. And since 13 is higher than 12, then it's going to go to the second chunk. So instead of going through and looking through every single item or element, what it would do is it's going to defer to the highest, the maximum value in the chunk, the first chunk, and then that's going to be the marking point. And it's going to, if it's higher, then it's going to go to the next chunk. Okay. So in the example here, we're looking for the number 34. So since 12 is lower than 34, it automatically jumped to the second chunk and it would find the 34. So it's definitely faster than your linear search. Okay, so it first have to compare the key value to the maximum value of the first chunk, which is 12. Since it's higher than 12, then it's going to evaluate the maximum value of the second chunk, which is 37. So it knows, so then it's going to go to the middle of that chunk or closer to the middle of that chunk to find the 34. Because 34 is lower than the 37, as 37 is the maximum value of the second chunk. Now, let's say if we have to find the number 33 in that same container, well, first it's going to compare 12, and it says 33 is higher than 12, so it's going to go to the second chunk. It's going to then compare with 37. So because 33 is less than 37, then it's going to move back by each element, and then it's going to find. So instead of iterating through every single element, we can zone in on a subset of that container and then iterate through it through comparison, after comparison. Okay? So if you look at example program online, you would probably see it labeled as jump search. Okay. So let's look at the next question. For number 2, it asks you to note the similarities and the difference between linear search and chunk search. So in the chunk search, the collection is divided into chunks by taking the square root of your input, which is the number of elements that you have in the container. Then the search key is compared to the maximum value of the first chunk. If the search key is greater than the maximum value of the first chunk, then it's going to look at the second chunk, and so on. If it's higher than the maximum value of the second chunk, then it's going to move to the third chunk, and it will continue to do that to look for the key. And in the linear search, each element is compared as if you were looking at an unordered linear search by simply iterating through the container or the array. It's going to evaluate one by one in an unordered linear search. In the ordered linear search, the elements is compared as to the middle point. If it's higher than the middle point, it's going to move to the second half and do the iteration there. If it's in the first half, then it's going to terminate as soon as it finds it. So if you compare the two, chunk search would have less comparison because we can now break the container into subgroup, and instead of evaluating every element, we are evaluating the max element, the maximum number in that subgroup. So it's definitely more efficient. It saves you time when you implement chunk search in comparison to linear search. Any question with these two? So I'll leave it there for a little bit. And you can pull the details also from the notes, or you can summarize it. You don't have to put verbatim answers there.
Would this be more efficient than
Can you repeat the question?
Linear search?
Can you repeat the question, Scott? Say it again.
Yeah, would this be more efficient than the ordered linear search?
Yes. So if you're looking at, like, let's say if we're looking at a very large container, right? Like 500 elements, 1,000 elements. Let's say 1,000 elements. Okay. So you would take a square root of 1,000 to chunk, right? And in that, I will show you how the number of comparison would be for a certain number of elements, right? So in the ordered linear search, it still have to iterate through. So let's say I'm looking for the number 400. It's going to have to iterate through up to 400 from 1 to 400. Okay. So that means that I would likely have about 400 comparison for the ordered linear search. Okay. Now in the chunk search, when you take 1,000 elements in the container, you take a square root of that, then you're going to chunk it. So it's going to go to the first chunk, okay? And it's going to look at that maximum value. So that's 1, right? And it's going to go to the next one. It's definitely a lot less than 400 comparison using jump search or chunk search. Okay. So we'll do the calculation shortly. So if you ask me which one I would pick that would be more efficient, I would pick the chunk search, definitely. Binary search is better, but chunk search is better than the linear search. Okay. Any other questions with these two type of search algorithm? And depending on the programming language, right? Some programming language would have built-in search algorithm to the library and some do not. Like I know C++, if you incorporate some, like if you include algorithm, you can have the sort mechanism. And then, but for Python, I know that Python has some of the algorithm already built into the methods for the library. So, and you have to ask yourself, well, what kind of algorithm is it using? So if you use that in your, when you're writing an application, is that efficient or not, right? So when, if you're choosing to use a built-in method or function, then is it efficient enough? Is it doing, what kind of search algorithm is it doing? Or what kind of sort algorithm is it doing? Okay. So now, sorry about the crazy highlight. Let me unhighlight this. Okay. For number 3, it asks you, what is the purpose of having a worst case analysis when analyzing an algorithm? So when you are analyzing an application or an algorithm in your program, you have to think about the worst case scenario. Okay. And after it goes over and talk about this, it talk about analysis of algorithm. And I'm going to revisit this because one of the lab we touch on this. And when you take 17C or 18C, sometimes they go over it in Java, but in 17C, I know Dr. Lair spent quite a bit of time on this. So in computer science, time complexity is the computational complexity that describes the amount of time that it takes to run an algorithm. And it is estimated by counting the number of elementary operations performed in an algorithm. So if you simply have a loop, like a for loop, right, to iterate through 100 elements, it's simply a linear function, f of n instead. So that means that that is going to be calculated based on the number of input because you only have one operation, which is your that would just be O of n because you simply dependent on the number of input for the iteration process. Now you would consider the worst case or the worst time complexity, which is the maximum amount of time that's required for the input of a given size. So you can have an array of 10 elements right? Or in some case, you would have an array of 1,000 elements or 1,000,000 elements. So your size is different. Your input size is different between 10 and 1,000,000. Now, in the worst case scenario for the 10, it has to go, for the linear search, it has to go through the entire array, which is 10. In the worst case scenario for the 1,000,000 elements, it has to go through 1,000,000 elements in that container, right? Now, when we evaluate, we look at the worst time complexity. For the average case complexity, which is the average time that it takes on the input for the given size, it's not often used for documentation purposes or comparison purposes between one application to the next when we're analyzing the algorithm. And when we look at the T, the time complexity, we look at the function that would be the function of the size of the input. So earlier I said, well, the 10 elements, right, that will be 10 inputs compared to 1,000,000 elements, that will be 1,000,000 inputs. Okay. And in the case where you have nested for loops, where you would iterate and then you would nest another loop inside it to also iterate from the inside, then you would have your big O, they call this big O, is going to be n squared, in compared to when you have only one for loop in your algorithm just to iterate through a container, that will be O of n. So the big O notation is a way that we can represent time complexity that would be addressed as a function. Okay. So like the linear search example, we know that it would just be the input. So your big O, that will be n, or O of n. Okay. And then later on, when we talk about binary search, this is for the binary search. So to answer the question, we would say that the worst case analysis aims to determine the slowest possible execution time for an algorithm. And the worst case, I should put a hyphenate there. The worst case analysis is useful because it tells you no matter what, the runtime of the algorithm cannot be slower than the bound derived. So an algorithm with a good worst case runtime will always be fast. On the other hand, the average case analysis aims to determine how fast the algorithm is on average for a typical input. And it may be the case for the worst case runtime of an algorithm is quite slow, but in reality, the typical input would be much faster. So if you use average case analysis, that would not really clarify how good of an algorithm that is. So using the worst case, you know that that would be the most or slowest possible time for execution, and that's going to be your bound. Okay. So we want to derive analysis from the worst case scenario, not the average, because the average can show it simply shows the typical input. And sometimes in your worst case, it might be slow. and typical input might be fast. So in most university, they dedicate a whole class to algorithm, right? In that class, the programming language of choice will be used to write algorithm for different problems. And then for each of the problems, you would have to analyze based on your input and the algorithm that you implement in your program. Okay, so mathematically, we need to kind of see the comparison across, right? So let's look at the next question. For number 4, it asks you, oops, sorry. So when you're searching through 2,000 elements in a vector, assuming that the system takes 0.5 nanosecond to search through each element, how long will it take to search through the entire vector using, I forgot to put, using linear search. Okay. So in the worst case scenario for linear search, in our question for number 4, we would have to search through all 2,000 elements. So we would then take 0.5 nanoseconds times 2,000, which gives us 1,000 nanoseconds. And you can do the conversion and use a calculator to convert. So this would be the amount converted to minutes. And you can leave it at 1,000 nanosecond. That will be fine. Okay. So you simply take the 0.5 nanoseconds and you multiply it by 2,000. Why 2,000? Because for the linear search, in the worst case scenario, it looks through the entire container. So that would give you 1,000 nanoseconds. So when we look at solving a problem, you would break it into 4 steps. Okay. The first step is you need to design an algorithm or derive a step-by-step procedure for solving the problem. Then you need to analyze how efficient is that procedure. Third, you need to implement the procedure in a programming language like C++, Java, Python, etc. Or in my student case for CIS7, LC3. Then you would test the implementation. So when we look at the algorithm, okay, the absolute execution time of the algorithm would depend on numerous factors. One, we talked about the size of input, right? The length of 10 versus 1,000. 2, algorithm that is used to solve the problem, what kind of algorithm it is. Okay. And earlier we saw that chunk search is better than linear search, and then we will talk about binary search, how that is better. And so then when we implement the programming language, that programming language is used to implement for the algorithm, it can vary from one language to the next. Okay. So if you're looking at the old legacy language like BASIC, that is much slower than C++. Okay. On how that language is interpreted and how that program can be compiled. And then we have to look at the factor that the quality of the implementation, is it good? Is the code tight? Or is it sloppy code? And sloppy code, right, would cause inefficiency. And then one of the factors we cannot forget is the machine that's used, the processor that's used, processor speed that's used to run that program. So here it talks about the worst case scenario. That's where I got my answer. Okay. And worst case analysis are interesting in their own right, easy to perform, easier to measure than the average case. And it's indicative of average case performance. Worst case analysis tend to be performed most often. So it's widely accepted. Okay. So we already touched on linear search. And then next we're going to talk about chunk search. Okay. So in consideration that you have a large container where you would have to use big chunks, your C is going to be large, right? And we talked about how we would take square root of your input to derive the size of your chunk. So here it says that searching for an element in the question within a very large chunk would require many such examinations, considering the case of C is n. In the worst case, that will be n divided by C or n divided by n, which is one element examination would be spent finding the right chunk, at least one. Okay. So while C is equal to n examinations that would be spent searching within the chunk for the total of n plus 1 compares in the worst case. Okay, so what we would see is after we divide it into the chunks, to look at the number of comparison, you would take 2, you would multiply it by the square root of n, which is going to be your chunk. That would give you the number of comparison or examinations in the chunk search. So the example here on page 5, it tells you that if you have 1,000,000 element in the ordered linear search, that will require 1,000,000 element examination in the worst case scenario, while chunk search would require approximately 2,000 examination in the worst case. Okay. And that would be 500 times faster. How do they get the 2,000? Well, we would take 1,000,000, we would take a square root of that, and then multiply it by 2, which gives you 2,000 examinations for the chunks in the worst case scenario. And 2,000 is definitely a lot faster than 1,000,000. Okay. Any question with this? So now let's look at the next question. For number 5, if an application uses chunk search to find matches in 100 elements in an array, what is the chunk size in the worst case scenario? So your input, your n is 100. To determine your chunk size, C, you would take square root of n, which is square root of 100. So you can have a chunk size of 10 elements each. And that means that you would have 10 chunks, right? Then for number 6, actually, let's go over binary search first. So let's look at binary search first. So in binary search, we operate a little bit different than the chunk search. So in the binary search, it's going to take the container and it's going to cut it in half for the first round. Then from there, it's going to take each half and divide it again into half. So it becomes a quarter. Okay. So first we divide it into half, take each half, divide it into half again, which gives us a quarter. And then take that quarter and divide it into half again. And it's going to keep doing that until it gets down to a single element. And then it's going to traverse back by doing the evaluation or the examination. So in such case, when we keep dividing it by half, we would have the log 2 of n is going to be equal to k. So for the log 2 of n iterations that need to be performed until the array can no longer cut into half. So when it gets down to, it keeps dividing into half until it gets to the smallest, which is a single element. Okay. Then that would make your T of n is going to be equal to log 2 of n. Okay. And to calculate that, we simply can do natural, you can plug this into the calculator like this, or you can take natural log of n divided by natural log of 2. That will be for the binary search. Okay. And is it faster than the chunk search? Yes, it is. So going back to the last example we talked about between the linear and the chunk, if we use the same example, if we have a million element, the binary search would perform only 20 comparison in the worst case scenario. Okay, so you can take a million, you can do natural log of a million divided by natural log of 2, then you would have the number of comparison that you would that it needs to compare for a million. So 20 comparison is definitely a lot lower than 2000 comparison in the chunk search and a lot less than 1 million comparison in the linear search. So binary search is the best out of the 3. Okay. So this table gives you some brief summary on the comparison of the 3 algorithm for the search. Okay, so with that said, you already know the formula there. Let's solve for the next one. For number 6, in an array that has 8,400 elements, how many comparison must be performed for the binary search to find the result in the worst case scenario? So your T of n is going to be log 2 of n, or natural log of n divided by natural log of 2. And natural log is ln. Okay. So that means that we would have 13 comparison for 8,400 elements in the worst case scenario. And you will see questions like this on quiz and final exam, so make sure you know how to calculate the number of comparison using different search algorithm given the number of inputs. And for the same case with 8,400 elements, how many comparison is going to be performed using chunk search? And sorry for the enlarged font. I used to teach this in the classroom, so, and when I project it, I want to make sure people in the back could see it. So your T of n is going to be 2 times square root of n. So your chunk size, which is square root of n, that will be 91. And then we would take 2, multiply it by 91, which gives us 182 comparison. And that means that it's what, 10 times, more than 10 times slower than binary search, right? Using chunk search in this case. And then for the linear search, worst case scenario, we have to go through the entire container, which gives us 8,400 comparisons. So that will be the slowest out of the 3. Questions for number 6. I see a chat question. Oh, just a comment. Okay, I'm glad it makes sense. Okay. So make sure we know how to do this. Okay. You will see it on the next quiz and also the final. And that is for the search portion of the lecture. Then now we're going to move to the sort. So sorting is where we would take the values in the container and we would organize, rearrange the value so that way it would be arranged in a specific manner. Usually we would go from ascending sort, meaning that we're going to go from low to high, or we can go descending, or we would go from high to low. And I love Python for the fact that it has all of this stuff built in, so you don't have to write your own. But again, we wanted to talk about different type of search and sort algorithm and see which one would be the best so we can make the appropriate choice in the algorithm implementation. Okay, so the first one is insertion sort. And this would be like how, if you ever play cards, when you dealt with the cards, right, you would take the cards and you would arrange it based on the order. So let's say that I would get 34, okay, then I would place the second card compared to the first card when I receive it. Okay, so if it's lower, right, then I would put it before the first card. If it's higher, I will put it after the first card. Okay, and as you go about, you would then insert the value based on the comparison of the previous. Okay, in the position of the actual element. So here, let's say that we received a 34, then we get a 16, right? This is the unordered way. This is what we receive. 16, then the 12, 11, and so on. So when it sorts it, it's going to take that 34, okay, and it's going to use that as the first comparison point. Then what it's going to do is going to take that 16 as the second value. Then it's going to say, is it higher or lower than 34? If it's lower than 34, it's going to put it before. Okay, so in the first round, we received 34 and then 16. So in order to insert this, right, it's going to compare to 34. If it's lower, it's going to put it before 34. Now, in the computer, there's no magical swap, okay? When you do these things, you have to think about location in memory where you would move the values about, okay? So in order to get from here to here, what I need to do is I need to move the 34 over to the right, to the second element, take the 16, move it to the 10th, from the 10th, move it over to the first, okay? Because you can't just swap it like how we would physically do it with the card. That's not a thing in the computer. We have to think about where you would put it in the meantime when you do the swap movement, triangular swap, okay? So after we move the 16, then we receive the 12. So the 12 now is going to be compared to the first element, which is 16. And is it higher or lower? It's lower, so it's going to move the 16 over one spot, and then it's going to insert the 12 into the 16's original spot. Okay. And then again, we receive 11. 11 is now compared to the 12. It's lower than the 12. So we got to move everybody over by one location, then insert the 11 in the front. And that is what we call insertion sort. And it's going to keep doing that. Now, when we get to 54, right, since 54 is higher than the rest of them, it stays there. And then it just moves over next to the 34. Then the 10 is going to compare to the 11 because that's the first element. Then if it's lower than 11, it's going to move 11 over 1 and then put the 10 in front of 11. And so on. Okay. So this little image here, this chart kind of show you on how it's going to do each round. And this is insertion sort. So in the face of the K of the algorithm, the kth element of the array is inserted into the sorted list from the first K minus 1 element of the array. So in the insertion sort, in the phase 1 of the algorithm, the first array element is examined. In the phase 2 of the algorithm, the second element is examined against the first element, right, for higher and lower. And it's going to use the first element going forward. So we still have to answer these. I forgot about these, sorry. All right, for number 7, we would do the same thing as number 6. So for the search of 9,750 elements, how many comparison must be performed for the binary search? So you can take natural log of 9,750 divided by natural log of 2, which gives you 13 comparisons for A. For B, you would have a chunk size by taking square root of 9750. That will be what, 99? So we're going to round it up, right? And then for the comparison, you would take 2 times square root of 9750. So that will be 2 times 99. And then for C, that will just be 9750 as it is the linear search. And sorry about the number 8, little lengthy. So there's a question, says, when getting the total of comparison for the searches, should we always round up the decimal when getting the final result? Yes, because that would be in the worst case scenario, because if you round it down, you actually reduce it to could be one less, right? Because when you look at the element, it's a whole element. It's not just half of an element. So you would need to round it up, because earlier when you look at the 8 elements, we're going to chunk 3, 3, and a 2. Okay? So we would round it up to a 3 instead of giving it 2, 2, and so on. Yep, no problem. So when we look at the given array for number 8, we would see that it is not sorted. We need to apply insertion sort. So the sort would begin, and you don't have to put the verbatim. You can put down the steps on how it would sort. That's fine. Okay, I just use the table, or yeah, the chart, so it can show you how the sort would begin and how it would go through. So it would start with looking at the first element, which is 87. And it's going to take the 6, which is the second element, and compare it. Okay. And since 86 or 6 is lower than 87, or 87 is higher than 6, 6 is placed before 87. So that will be the first iteration. In the second iteration, 14 is our third number, and 14 is going to be compared to the 6, which is the first element. So if it is higher than the first and less than the second, is placed after the first and before the second. So that means that the 14 is gonna go in after it's gonna get inserted in between 6 and 87, because 14 is higher than 6 and lower than 87. And then it's gonna take the 6C. 6C is gonna compare to the 6. And since it's higher than the 6, it's going to look at the second element. It's going to be higher than 14 and lower than 87. So it's going to insert between 14 and 87. And it will continue to do that. Okay, so the first round is that use the first 2 number, compare which one's higher, which one's lower. The lower one goes first. And then it place the higher one after the first. Then take the next number, compare it to the first. If it's lower, then put it in front of the first. If it's higher, put it after the first. Or if it's also higher than the second value, then it's going to put it after the second value, and so on. Now, manually, when we move this, right, we can't just swap it back and forth like how we would look at this table. Like I said, we have to think about how we would use a variable or something that would represent a location in memory, put it there, and then do the swap. Okay. Any question? And you don't have to do the whole entire array. I just want you to grasp the idea of how insertion sort works. So you can go through like the first few iteration, and then as long as you understand how that is, I'm okay with that. So like I showed you there, I went through and I show the first few steps. Okay, any question with insertion? All right. So here it tells us that in the worst case that's given, right, you would have n minus 2 plus n minus 1 plus n, and to get the total number of elements that will be examined. For the selection sort, which is another algorithm, it's gonna look at the list of elements and it's gonna select the smallest one and swapping it with the first element of the list. Okay, so we would have n minus k plus 1. So let's say that this is what we receive: 34, 16, 12, 11, 54, 10, 65, and 37. Okay, so the lowest value, that's going to be 10. Okay, and 10, that 10 is going to be moved to the first position of that container. So it's select the smallest value and then swapping it with the first. Then after that, the next smallest is going to be 11, right? That will be higher than 10. So it's going to place 11 after 10. And then after that, that will be 12. That's going to go there. And then 16, it's going to select 16 and put it after 12. And then 34 after 16, 37 after 34, 54, 65, and be done. Okay. Now in this one, we have to zone in on the lowest value, and that lowest value is going to get organized and it's going to arrange all the subsequent value from the lowest value. So important note that this says that it is the same sum as given by the analysis of the insertion sort, only written backwards. So for number 9, we're going to do selection sort procedure. And in order to program this, you have to understand how it works mechanically, right? With the movement manually, and then that way you can implement the procedure. So here is our given values for phase 0. In the phase 1, which is the first iteration, it's going to begin with looking at selecting at the smallest value, which is 2. And swapping that 2 with the position of the first element, which is 41. So the 2 move over to the 41 and the 41 move over to the 2. Now, when you do this with C++, right, we have to have a temp location, move the 41 to the temp, and then move the 2 to the 41, and then move the 41 from the temp to the position of the 2. Okay, and I call it triangular swap. Okay. So the 2 is the smallest value. It is swapped with 41, and 2 is now the first element. Second iteration. Then it's going to select the element from the remaining n-1 elements and swap it with the element in position 2. So the next one is going to be 3, right? And so it's going to do the 3 with the 7 because the 7 is the second spot. So I'm going to move the 3 to the 7 and the 7 to the 3. So 3 is moved into the second element and 7 takes the position of number 3. And it will continue after that. So after that, right, we would go to the 6. 6 is going to swap with 12. So 6 move over to 12, 12 move over to the spot for 6. And then we would then move the 12 with 83. And then move the 16 and so on. So it keeps swapping until it's finished. Any question with selection sort? Like I said, you don't have to put verbatim, but I want you to show me, right, that you understand how the selection sort works. So you can describe the step on what's happening. Okay. So now, then we're going to talk about merge sort. And this is divide and conquer algorithm. Similar to what you've seen with binary search. This is how we can sort by subdividing. So it start with the unordered list, and it's going to divide that into 2 halves. And then it's going to keep dividing it until it cannot divide it anymore. And when it got to the smallest unit in the division, it's going to compare. Okay, so to illustrate this, let's look at page 8. So the original list, you have 19, 3, 12, 5, 7, 22, 18, and 4. There are, 8 elements. So it's going to cut it into half, 9, 3, 12, and 5 on the left. And the second half, it's going to be 7, 22, 18, and 4. From the first half, it's going to divide it again into 2 more halves. And the second half on the right, it's going to divide again into 2 more halves. And then it's going to divide those into another half, which then we would have 19 on 1, 3, 12, and 5. Okay, so it's subdivided until it gets down to the single element. There are 8 parts. Then it's going to take a look at the 2, right, 19 and 3, and it's going to compare which one is smaller. The smaller one is still going to go in front of it, and it's going to merge it back by combining the halves back into the entire list. So 3 goes before 19. The 12 compare with the 5. So 5 goes in front of the 12. 7 compare with 22. 7 is lower, so 7 goes before 22. 18 compare with the 4. 4 is lower, so 4 goes in front of 18. So at that point, it's already merging, right, the single element back into double element sublist. Then it's going to take the 2 element list and merge it into a 4 element list. So we would then compare, right, 319 with 512. So 3, which is going to be lower than 5, so 5, and after 3, 12 after 19. So as it merged back, it's going to compare these elements against these elements and then put them in the proper ascending order. Okay, and then once it gets to the 2 halves, it's going to then merge again, and as it merge, it's going to reorder them, rearrange them from the lowest to the highest. So that's why they call it merge sort. So as it merges, it sorts. And it is faster than insertion or selection sort. So in the insertion sort, we look at the comparison, the worst case scenario. In the insertion sort, your O would be n squared. Your big O for selection sort, that would also be n squared. Your merge sort would be n log of n. And there's one more. Your quick sort would be n squared, which is the same as this in output. So with the selection sort and the insertion sort, you're going to get about the same. Okay. Any question? Okay, no question. All right. Let's do number 10. Given the data, provide the explanation on how merge sort is applied. Okay, so we have 30, 5, 19, 66, 4, 10, 28, and 6. So we would have the list first gets divided into 2 equal pieces. Okay, so we first would take that list and we would have 2 halves. 35, 19, 66 on one half, and the other half would be 4, 10, 28, and 6. Then it gets divided again into 2 additional halves. That will be 30 and 5 and 19 and 66. 4, 10, and 28 and 6. Then after that, it's going to keep dividing one more time. Let me move this to the next page, okay? So you can see it together. So once it divided into single element, we would have 35, 19, 66, 4, 10, 28, 6. Then it's going to compare and merge in order. So the 5 is going to go in front of the 30, 19 is going to be in front of 66, 4 in front of 10, 6 in front of 28. Then after that, I don't know why I put those things there. After that, it would merge and order again. To combine the 4 sublists to 2 sublists. So we would have 5, 19, 30, and 66. Then we would have 4, 6, 10, and 28. And then after that, it would merge one more time, and it would then order as it does the merge. So it would be 4, 5, 6, 10, 19, 28, 30, 66. Okay. Combine 2 sublists into one list. So 4, 5, 6, 10, 19, 28, 30, and 66. And this is merge sort. And in C++ book, it's referred to quick sort. Same. Okay, any question? So divide and conquer. right? Divide it down to the single element, merge and sort together. When it merge it back, it's going to sort. So it's going to combine all the sub lists or subparts back into the original list or the list that's ordered. Any question with this? I want to reserve some time to talk about the lab. So, because we're not going to meet on Wednesday, for those of you who missed my announcement earlier, Wednesday is a holiday, Cesar Chavez Day. So the college or our district have a floating holiday. So that means that we're not going to have class in session on Wednesday, the 31st. Okay. But I need for you to, you don't have to put those. I was just playing with the table. You will need to at least do, I want you to do the lab so that way you're familiar with how to write it in C++. Okay, it's important that we do that. And I don't want it to push it to the last, the next few weeks, because we would have other things that we need to address. And also we will talk about your project when you come back from spring break. Okay, so no class on Wednesday. Take a day off, relax, right? So I'm going to touch on the lab now. So if you want, you can download the lab, and then, you know, I can give you the preview. And it's really easy, the lab. Okay, just like what we just do right now, but with a little bit of programming. Any question as far as the assignment goes? Okay, save your work. If you finish, you can submit it on Canvas. And then we'll touch on the lab next. Okay, so here's the lab. And I thought I had a video from last semester, but something happened to my video. I couldn't find it on YouTube. So maybe I didn't upload it. It was just on Zoom. Okay. So instead of omitting the lab, I thought about it and I feel that I think you should learn how to do search sort algorithm. So at least it gives you the introduction into doing that. And some of you probably have done this before, but it's a good review anyway. Okay. Hold on one second. Let me get to my folder. Okay, so now I'm going to talk about the lab. So at the beginning, it's going to show you the information about binary search. We just touch on binary search. It gives you an example of how it goes through numerous iteration, like what we talked about. It cuts it in half and then divide it into half until it can't divide it anymore, right? But in this case, we have 2, 5, 8, 12, 6, 23, 38, 56, 72, and 91. Noted that this array is sorted. Okay. So in order to really determine the mid value, we should have a sorted container to start with. Otherwise, right, if you have an unordered container, you need to, you know, include algorithm, sort it, and then find the middle point. Okay, so here we would then have a middle element, which is 16. And what we would do is, since 23 is larger than 16, then that would be the higher part. This is the larger part of the array. So if we're seeking a certain value, for example, if we're seeking number 56, it's going to go to the second half to look for that, right? But it's going to, in binary search, it's going to keep iterating. Sorry, my dog tails. It's going to cut it into halves until it gets down to the single element. And then from there, it's going to be able to seek for the value. Okay. So I'm going to talk about the program now. So here's the program in C++. Okay, that's fine, Thomas. No problem. Okay. So in this particular program, what we see is we are using iteration, and we are going to cut that array into half until we go down to the single element, like what we talked about. So here you would include algorithm, you would include array. And in the comment, it shows you, and you can enlarge the picture from the lab document. Sorry that it's small, I try to fit stuff onto one page. You have a function, binary search, okay? And you're gonna pass the array, okay, L, R, and X. So here what you have is you have a while loop. And what you're gonna do is you're gonna set up the while loop so that way if L is gonna be less than or equal to R, if that's true, then it's gonna execute this body. That's gonna be your length, right? Plus R minus L divided by 2. Okay. Now, if you look down here, what we're doing is we are going to initialize the array over here. Okay. Now, in the while loop, you also have an if statement. It's going to check to see if X is present in the middle. So M is going to be the middle point, right? So when you're cutting that list into half, you basically identifying where that middle point is going to be. Okay. So X is the value that you're going to search for. We're going to look for number 10. And so in the if statement, it's going to see if X is equal to that middle value. Okay. In this case, that will be your number 4. Okay. So it's going to compare the 10 to the 4. And if the middle point is less than X, it's going to go to the second half and it's going to search for the actual value there. And in this case, it does that. It actually, X is larger than the middle point, right? Which is 10. 10 is higher than 4. It's going to go through and it's going to seek for the key in the second part of the list. Okay. So here in the main, we initialize our array. We also declare the search value, which is 10. And for the n is going to represent the size of your array, or the number of elements, I should say. and then your result is going to store the output from your binary function. Okay. And then we simply see out. So when we run this, it's going to tell me that this is going to be present at index 3. So here is 0, 1, 2, and index 3. It found 10. Okay. So this allows us to really identify the location of the key value that we're searching for. And this is an iterative approach. So in the lab, you simply refer to the example program for the exercise 1. And then for number 1, you are comparing, or you're using 5-element array. So you just need to calculate, right, how many comparison for the 5 elements array. So if you plug in log 2 of n and n is 5, or you can do natural log of 5 divided by natural log of 2, which give you a little bit over 2 comparison for the overall array, right? Because think about it, it needs to compare from the middle. It's gonna from the middle, and it's higher than that. So that's one comparison, right? And then where's the middle? And then that middle is gonna be lower or higher. So since it's higher than that middle point, that's going to be a 2 comparison for that program. Okay. So for B, we simply take that array and we would divide it from a 5-element, right? Explain the functionality of the algorithm. So 4 is the middle, 2 3s are on the left, 10 and 40 is on the right. It's going to compare the 10 to the 4. Since the 10 is greater than 4, it's going to go to the right half, and it would be using the second iteration to find the number 10. Okay. So with binary search, you would start with cutting that list into half, or where that middle point would be. And then from there, you would section that. So say, is it lower or higher? Lower is on the left, higher is on the right. L for left, R for right, like what we've seen in our program, right? Okay. And then M is for the middle. Okay. So in the first exercise, you simply just need to run the program, calculate the number of comparison based on the given formula. Then you just explain the process and how it's finding that 10 in the array by cutting it in half, which is where the middle is, and then be able to compare. You can leave it as a whole number. It's fine. I just copy and paste the value in there so you see a long, lengthy number, but you can round it. Okay. Whole number will be fine. Okay. Okay. Then for example 2, you're going to see a very similar program, but in this one, you're using recursion in example 2. Sorry, it's a lot today, I know, but that way, I wanted to clarify everything and making sure you understand. So in example 2, what you're doing is you have a similar program, okay? Now, you are also cutting it in half. So you have the middle point, which is going to be the left plus r minus 1 divided by 2. Very similar to the other one, you would have an if statement. That midpoint is going to check to see if it's equal to x, which is your key value that you're seeking. If it's greater than x, then it's going to return, right, the binary search. So here is where it calls itself, okay? That makes it a recursive program, right? Because this is your function, and when you're calling itself, okay? And then, so here we would return the array left, mid minus 1, and the x. Else, we would return the output from the function. That would, the parameter would be the array mid plus 1, which is the right side, right? This represents the left, okay? And then otherwise it would be the right. And then in the main, we simply initialize our array. We declare our key or seek value. We specify the size or of the array or the number of input. And then we would have result is going to store, right, the output from the function. And when we run this, right, it's still going to give us the same output, of course, compared to the last one. So you would first check out example 2, run the program, describe the main functionality of the program, how the binary search is implemented in the program. So look at the binary search function, right, how it's calling itself for recursion. In 2B, you just need to compare the two programs and explain to me which one is more efficient. I think we spent a little bit of time talking about recursion and iteration. So tell me which program would be more efficient. Okay. And if you're not sure what's happening in the program, make sure you read the section. It gives you the procedure on what was implemented. Okay. Then for the jump search, which is the next program, and we talked about the jump where it chunk it, right, into subgroup. And then it's going to look at the maximum value in each chunk. Okay. So here it tells you the step on what's happening with that container. Let me show you how the program looks like. And this is often referred to as jump search, or chunk search is the same. Okay, so here we have a function called jump search. Okay, the program looks kind of like the other ones, but a little different in that we're going to work with the chunk here. Okay, so for the function, we're going to use array as ARR. We're going to have the int x for the seek value, and int n is going to hold the input. So when we use int step here, that's going to be square root of n. That's going to give you the chunk. Okay, that's going to be it. Step is going to store the chunk. And then we have a while loop. Okay. And we're gonna use the while loop to step through the chunk in the actual program. Okay, so here in the while loop, the previous is gonna be step, and we're gonna increment that. So what we're doing is we're jumping from one chunk to the next by incrementing. Okay. So what it's doing here is we are going to find the block that we can go to look for X. So first, in the procedure, you have to find the chunk where X would be. Then you would look for the X in the second while loop. Okay. So when it find the chunk where that X would be, then it just simply use a linear search to look through it for comparison. Now in the main, we would initialize our array. We would specify our X, which is the key search value. We would specify the number of input. And then our int index is going to store the result from jump search. And then we would simply print out the value for the index. So it will tell me that the number 55 is at index 10. Right there. Okay. So I want to show you how you can create a program in C++ for jump search or chunk search. So for exercise 3, all you're going to do is you are going to run the program, give me a screen capture, determine the chunk. So there are 16 elements. So if you take square root of 16, you should get 4, right? So the chunk size is 4. So it's going to chunk like the first 4, then the next 4, and so on. How many comparison will you need? 2 times square root of 16, that will give you 8. And for 3C, you just need to explain the program functionality in the algorithm implementing. So if it helps you, you can read the previous section here. It talks about the jump, right? How it jumps through, or you can also read the comments of the program that gives you the purpose or the functionality of that section. Okay. So that would be for number 3. Very much like the calculation we've done earlier. Okay. So in the worst case scenario, it needs to perform 8 comparison in order to find the 55 in the 16 elements array. Realistically, what you're going to have is you're going to have 1, 2, 3. It should find it by the third one. It goes to the chunk, so that's 3. Then it's going to look at the maximum value and then do the linear search. So yeah, at about 5 at the most, if we manually count the process in that. Okay, because we have 1 comparison here, 1 in this chunk, because it's going to look at 13, so it's not there. Then here is the number 3 comparison. Then when it gets here, it's going to do a 1 and a 2 and a 3. So yeah, I would say like 5 to 6. And it would find a 55. So in the worst case scenario, it will be 8, but it's actually like less than that. Yes. In this one, we're not using a set, so you can have repeating numbers. Yeah. Now, in the case where if you're finding the key of a repeated number, right? It would just, let's say if I'm looking for number 1, it would identify both of these as they would be the same. Ideally, you shouldn't use repeating number, but it's not a set, so you can use repeating number. If you look at like real world data, yeah, you're gonna have repetition in values, of course. Okay, like, you might have employees that have the same annual income as others. Okay. Okay, I have about 10 minutes left, so I'm gonna touch on the last number 4, which is long. Okay. So let's see, 4, 5, and 6. Okay, I'm going to try to do the last few. Okay. All right, quick sort. Quick sort, what we talked about earlier, that will be for the next program, exercise 4, that's going to be quick sort. Okay. Let me go. Sorry, my connection is not the best right now. Okay, so we're going to use sort, which is a built-in function in the algorithm, right? So here we would have just the main method, the main function, and then we initialize our array, we specify the size, we would do a sort, and we simply, in the parameter, we pass with the array name ARR and ARR plus n. So we want to sort through all the elements inside that array using the built-in sort. Okay. And so in this, the built-in is actually a default quick sort. So now when we have the for loop, we simply use a for loop to print out the sorted array. Okay. So we have a non-sorted array to start, right? As you can see here. And then we simply apply the quick sort or the built-in function sort, and then it gives us this. Okay. So the easiest way is to use sort from the algorithm STL. We've seen this before in our other lab, right? So this is how you can do a sort in any array. Okay. So here it shows you want to run that program, give me a screen capture, explain the sort functionality in the program, how the values are compared for order rearrangement. So here it talks about the details in the quick sort. It's different than the heap sort and the insertion sort. By default, the sort function uses quick sort, and what it is it's going to be very close to what you've seen with the merge sort. Okay. And when they implemented this built-in function, they implement what you see in merge sort. So explain how you do the merge sort. You cut everything into half and half and half, and then as it merges back, it's gonna do a divide and conquer. Okay, so it's gonna sort as it merges back. Okay, so explain the mechanism for quick sort there. Then So for this lab, let me see. Just do up to number 5. I'm okay with that. Okay. If you want to, you can do number 6. I'm not going to require number 6. Number 6 is a little long, but if you want to know how to write it. And I didn't screenshot this, so you can copy and paste it. But when you copy and paste, be careful with the symbol, okay? Because when it goes from Word over to your IDE, it might not interpret all the symbols. Okay, so on the next one, it shows you how to do selection sort. And for number 5, you are to do a selection sort. I want you to do this one because it shows you how you can move, right, when you swap the value. Like I've mentioned, there's no magical air location, right? We have to put it into the memory location, so that way we would do a triangular swap. Okay, so let me show you that in C++. Selection sort here. I might lose internet connection. I'm sorry. Just hopefully not. All right, we're almost done. A few more minutes and we'll wrap up. Okay, so on this one, we include algorithm, we include array. We have a voice swap, which is a function, right? And here you notice that we're using pointer. And these type of program, it's best to use pointer. And as some of you already took data structure, right? When you using data from certain location, a lot of the times we don't really move that data, we just point to it, right? So here you have a swap function, and you have a temporary location that's going to point to XP, and then XP is going to point to YP, and YP is going to be the pointer that's going to be for temp. So now, if you've done like other type of algorithm in like 17A class, you're going to see something similar to this. So here we define the voice swap, and then I have a selection sort function. Okay, and in this, what we're going to do is we are going to have a for loop, a nested for loop actually. And in the outer for loop, we would do the boundary of the unsorted array. And in the inner for loop, this is where we would determine the lowest value in that bounded area, because as it cuts it in half and half and half, remember that when we sort it back, we have to look at the lower value as we would select it, right? So when you go and you take that value and then you move it, you have to look at how the lower is going to get swapped into the position of the other. Okay, so here is where you would have the swap with the lower value, and then we would have another function that just simply print out, right, our sorted array. In the main, we initialize our array. We only have 5 elements. The int n is going to be the input or the number of elements. And then we call on selection sort, and we call on print array function. So when you do this, right, after the program is ran, you should get a sorted array, which gives you 11, 12, right, 22, 25, and 64. So it worked. Okay. So this one is when, remember, it select the lower value and then it swap it, right? So it's going to point to that value as lower. So in this, what we're doing is we have to implement these in order for the swap to occur. So first we got to set the boundary, then we got to identify the lower value, then we are going to do the swap with the lower value. So for 5, run the program, and then you are going to give me the screen capture, explain the implementation of selection sort algorithm in the program. And if you're not sure, go back to your notes and then look at what we did today with selection sort. How are the elements evaluated and rearranged, right? Look at the program itself on how you're using pointer and how you're using the nested for loop from the lowest to the highest value. And this program uses nested for loop, which makes it T of n is going to be n squared. So determine the T of n based on the number of program input. So you have 5 elements and you would square that, which gives you 25 is the estimated. Okay. So it would likely, at the worst case scenario, you would have 25 comparison as it sorts it. Okay. All right. So I am now at 8:01. I'm sorry to make it jiffy, but no class on Wednesday. Take a break. And then, I put this due on Saturday. So just take your time and work on it. And then you can submit it. And so that way you can understand how to do the sort and search. Okay. Have a good night. Type in your name in the chat, and I'll see you next Monday. Video will go up tonight.